So let's now proceed to see how we can make this even faster, right, by exploiting certain design considerations of the flop. So if you look at the flop, it's nothing but two latches back to back, right? So if you look at that, so this was phi and this was phi bar, right? Or if you want a positive thing, then this should be like this. So latch L1, L2, L1, L2. Okay. The issue with a flop is the edge is very hard. If you miss setting up the data before that rising edge, then you have lost that cycle. You have dropped a brick and it's gone, right? On the other hand, all I have to do is to move this latch somewhere in between here. Move this latch, so there is another combinational circuit after this, right? I have to just split the combinational circuit and move the latch around like this. The advantage with the latch is I don't have to set up the data before the rising edge. It's enough if I set up the data, or not rising edge, I will say sampling edge, right? I have to set up the data only before the sampling edge, which is a full half cycle away almost. If there is no, if there is basically zero overlap, right? And if the duty cycle is 50%, then it's a full half cycle away. So I get TC by 2 time approximately to, perform more computation. Okay. But of course, because of the problem of, so this is phi bar and phi again, right? This is a combinational block, right? So the idea here is now to take this and split it as follows. L1 running, let's say, on phi. Okay, now don't worry about whether it's a positive latch, negative latch. I'm going to split this combinational block as C1, then insert my L2 here. Okay, and maybe I should call this as L3 and L4. L2, C2, right? So this is combinational block C12, this is C34. L3, this is phi bar, phi. Then you get C3, L4 and C4, right? This is again phi bar. So what you have done is you have split the combination block C12 into two blocks C1 and C2 such that the delays add up. TPD of combinational block C12 is TPD of C1 plus TPD of C2. Similarly for C34. Okay. Now we'll analyze what the timing constraints are for this system, and we'll see how much of a gain we are able to get. Okay. Now, as I told you earlier in the when we discussed the hold time violation, right? This overlapping clocks is a big problem. So people generally try not to use just clock and clock bar, because inevitably the two edges will overlap at some point and you have a violation. So the best thing to do is to generate what is known as non-overlapping clocks. Two clocks, phi 1 and phi 2. Remember, see, there is nothing sacrosanct about having a 50% duty cycle. I can change my clock so that it has a very small, you basically have to be able to sample that thing in that setup hold window. It should be greater than that. That's all, right? So you can make the duty cycle very small and have two phases such that there is no overlap at all, which means that there can be no race condition that happens there, right? So therefore, what people do is they convert this instead of phi and phi bar, they call it phi 1, phi 2, phi 1, phi 2. How does the timing look? You just get something like this. Phi 1. Phi 2 is phi 2. What is the clock period? It's basically from rising edge of phi 1 to the next rising edge of phi 1. This is TC, right? And this period is basically the key non-overlap. Obviously, because the clocks are not overlapping there. Okay. So just to remind you, the setup hold window in red that we have to draw is actually here. For both phi 1 and phi 2. Because by default this a latch L1, L that I draw is a positive latch. If I want to make it a negative latch, I put a circle here. Then the clock will get inverted and then becomes a negative latch. Okay. So anyway, if I don't put the circle, it means it's a positive latch. Right. And these, again, this will be my setup hold window where data should not change. Right. So the point I was trying to make is, earlier our constraint was the setup hold window was here for a flop. Right. For flop, this is the window. That means data has to be set up before this rising edge itself. Now I have time till the clock falls, because that's the sampling edge for a latch, technically. So I have that much extra time to do something. Okay, and you can do many interesting things. So we'll first look at what the timing constraints are for such a system. Just like the previous case, we will try to draw it for both max and min delay in the same waveform, one after the other. Then hopefully we will get a clear picture of what's going to happen. So I'll have to draw this a little small first. This is my latch L1 with clock phi 1. Right, so this is combinational block TCD1, TPD, TCD1, TPD1. Okay, combinational block C1. Then I have L2, which is controlled by clock phi 2. Okay, then I have combinational block C2, then going to back to latch L3 controlled by phi 1 again. Okay, and then you have the following block and all that. This is C3 and so on. Okay, so first let's draw the two clocks. Right, this is going to be 0 all the way until next phi 1. Similarly, phi 2 will go high here. This is L1, L2, yeah. And somewhere here you will have the next L4 controlled by phi 2 again. Okay. So now let's look at D1, Q1, D2, Q2, D3 and Q3 and D4 and Q4. I don't think we'll need D4, Q4 and all that, but let's just look at this. Okay. So D1. So first thing, I am now trying to analyze my max delay constraint, right? What is the worst case thing? So what is the worst case? Is it that data changes before this edge itself here, somewhere here, or can the data change inside the stable state of the clock? It can change inside, and that is really the worst case, because I eat up some time and I still have to achieve this state, right? If you make the data change before the rising edge, then you have lot more time to finish your thing. Okay. So let's also, before that, draw our violation window. This is my violation window for phi 1, right? For L2 again, this is my violation window. Okay. So what happens is D1 is now changing somewhere inside here. Right, and this is my event 1 that has to be sampled and then held across, right? Oh, this is not event 1, I'm sorry. This is event 1. It had some other data. This is event 0, which we don't know what it is, so let's not worry about it. It changes to event 1. Every element has to now operate on event 1. Okay. So what will happen to Q1? First of all, what is the delay that will be involved? For latch L1, data has changed after the clock went high. TDQ, right? TCDQ or TPDQ, right? Correct. So this guy will start changing somewhere here, right? Q1, and this delay is what? TPDQ1 for latch 1, right? Q1 has changed. What happens to C1 now? It's a usual thing. It's just a combinational block. TCD1 and TPD1 is the delay that's going to be incurred now. So the moment this guy starts changing, you can have a very quick change. Okay, let's again, what's the worst case? Should D2 settle before the phi 2 rises, or can it go inside? Yeah, it can go inside, right? Same logic that you apply for L1, you also apply to L2, right? Therefore, this change is going to take it right in. Okay, and this delay is what? T propagation delay for block 1, TCD1, TPD1, correct? And this block is what? TCD2, TPD2, right? Now what happens to Q2 after that? sorry, Q2. At what point will Q2 start changing? Can it start changing here? Huh? Yeah, it cannot because the clock has not yet, the L2 is opaque. It is holding the previous state, right? It is holding event, which event here? Holding event 0 here, right? Even this was holding event 0, correct? So therefore, this guy will wait all the way till the clock rises. Right? Clock will rise and then you will see some change. And what is that delay? What is the contamination delay there? Actually, that's very interesting. What is the contamination delay there? T, CC, Q, because only after the clock edge rises will that thing go through, right? So you will start seeing some change here. Okay, we'll come to that thing and it will settle after, sorry, this one. What is this delay? T, what? P, D, Q, 2. Right? Now we will assume just one thing here, okay? In the next cycle, right, I want to just finish before this edge. I'll tell you why. There are two cases, okay? Some cases you can go into the next cycle also. That is called time borrowing, fine? But there are certain places, so essentially what I'm saying is, you can borrow within a half cycle, right? You can borrow time from phi 2 under all conditions. But to borrow time from the neighboring, from the next cycle, across cycles, you have some constraints. You can't do it in all systems. Okay, we'll look at examples for that. So let's assume that we got to finish by this particular time. So what will happen to D3? What will happen to D3? Yeah? Yeah. So it's going to basically go like this, right? And some contamination delay, and then it will settle to its proper state, right? Now, since I am assuming that this data change is happening before the rising edge of phi 1 itself, there is no setup time problem. It can happen just at that clock edge and it will still go through properly, because the setup time really is for the next guy, right? So there's no issue there. So don't worry about that. Okay. So now what is the timing constraint that I can write? Okay. What is this delay? T, C, what? TP, D2, correct? So what is the timing constraint I can write now on the clock? This entire thing should finish in one clock cycle. How far can this edge move if I don't want to borrow time from the next cycle? It should finish exactly at TC, right? So therefore, I'm just now going to write the sum of all of this. TPDQ1 plus TPD1 plus TPDQ2 plus PDQ plus TPD2. What's the inequality? Tc should be greater than or equal to this, right? This is my max delay. Okay. Now let's try to analyze the min delay constraint. Okay. What is the, when can D1 change first of all? Yeah. After the, correct. The time is not Tc. So again the assumption is this thing changes just at the clock edge. If you don't want to borrow time, yeah, but it is TPDQ1. That's all. The delay is D to Q, not C to Q. That's the only thing. Yeah. So it's just at the boundary for now. Okay. Yeah. Yeah. Which one? No. There's no negative. This is not a flip flop. It's a latch. Latches are by default, I told you, positive latches. When the clock is 1, all these latches conduct. Clock should be 1 for the latch to be transparent. That's all. It's not a negative latch. I told you that if I want a negative latch, I have to put a bubble at the clock. Only then it becomes a negative latch. Rising TPD2 can change, it can actually change even later. But now I'm just, sorry, I'm just imposing a constraint that I wanted to finish in that cycle. Because there are cases later where I cannot do this time borrowing from the neighboring cycle. Technically there is nothing that stops me from making TPD2 go all the way till this boundary. I can take it all the way till here. As long as that happens, it will still function correctly. Because that latch can sample it and hold it perfectly. No issue at all. But I am just imposing the constraint saying, right now I don't want time borrowing from neighboring cycle. What we are doing here, by allowing D2 to go into the, level 1 of phi 2, is we are time borrowing from the half cycle, which is okay, which can be done under all conditions. We'll see that example where it is not possible, where it is possible, then you will really understand. Okay. So now let's work under these constraints. Yeah. No. That's what I said. Look at where my violation window is. Violation window is on the falling edge. The latch samples when the clock falls, not when the clock rises. Yeah. There is no setup time constraint here is what I am trying to say. Because the setup time is actually on the falling edge. You see, this is my window. This is my violation window, setup hold time window. It's not here. So that is the key point about a latch. You have the on cycle to actually finish some more computation. Okay. Yeah. Yeah. L1 and L3 are exactly the same, assuming that there is no skew between the two clocks there. Well, if you're under at least under ideal conditions, they are the same. By design, they are the same. It can. That is what is clock skew and other things. Variations will be there. it can be due to other reasons also, but yeah, okay, by design they are expected to be the same. Yeah, Balaji, you had a question. Ah, yes. Ah, after. Yeah. No, 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 that's what I'm saying, because the latch is becoming transparent after that. See, let's assume, right? Let's assume that the change in a latch, okay, my clock is here. Let's assume that the data changed exactly here. Okay, this one is D1, this is D2. Clock 5-1, okay. I'll not say, let's say D1. Event 1, event 2. What is the aim? Ultimately, when the latch falls, when the clock falls, it should hold which data? 2. That will happen, right? Whether the data changes here or the data changes here, it doesn't matter. It has to hold, the latch has to hold the data for the remaining part. And if that data is held correctly, sorry, there is no problem. That's why in a latch, you should not, that's why I said even before I started, mark your violation windows correctly. Then you will not get confused. If there's no violation window, then there's no issue there. Data can change at any point. Yes, you may ask whether it is TCQ, I mean CQ or now TDQ. That may be the only difference. Right now we are saying it should not go after the falling. Oh, no, it should not go after the. Yes. So it cannot go all the way till there, correct? Yes. That depends on the splitting of the combination block, correct? Okay. So basically that depends on how much time you are borrowing. Right? You're trying to borrow time. What you're doing is, even before this phi2 went high, right? Usually you would have wanted to complete your operation before that. But now I'm saying, okay, I will borrow time in the on cycle of phi2. So question is, how much time can I borrow? That is also a constraint that we have to worry about. You're right. Okay. So now let's come back to our min delay constraint. Where can D1 change? D1 is supposed to, so if you look at Q1, the aim of Q1 is to simply hold this data for as long as possible, right? This is Q1, right? So this has to hold event 1. That's the aim. Then combinational block C1, L2, C2 will operate correctly. At what point can D1 change so that Q1 continues to hold L1? I mean event 1. After the hold time window, right? So now let's assume that my D1 changed here. It doesn't matter. Okay. So I'm coming all the way till here. Okay. And yeah, maybe I have to extend this waveform, but we'll do it. Right? That's my violation window for the next cycle. So D1 has changed, and then phi1 is going high in the next cycle. So what will happen? There's now going to be a clock to Q contamination delay, which is going to cause what? Q to change immediately, right? So you look at this. There is a Huh? Oh, I'm sorry. Okay, this is D1. Yeah, you're right. Okay, and this is, by the way, event 2. Event 2. Okay, so now Q1 is coming here, and then it starts changing this delay is what? T C C Q of latch L3. Okay, Q1 changes, therefore what? Yeah, no, Q3 changes, right? No, which one has changed? Oh yeah, sorry, Q1 has changed. I'm sorry, Q1 has changed. So now D2 will change after the contamination delay. Correct? So now you see what happens here. From this delay, from the earliest change of Q1 to D2, there is a delay of T C D. Oh, by the way, this is not T C C Q3 then. 1. Correct? So this is T C D 1. Right? Now, what is the constraint on D2? What should happen at Q2? Tell me. Look at the previous cycle here. What is the event that Q2 should have sampled? 1, right? So Q2 is expected to hold event 1 all through like this until the next thing. So this has to be event 1, right? But this is event 2 already, by the way, and so is this. So you agree that on D2, event 2 has now changed while you are expecting it to hold event 1 correctly. Right? So remember, this is, I'm showing it on a timeline like this, right? And unfortunately, maybe let me redraw it like this. That will really help. I'm going to call this again L1, this C1, and this back to L2, because we are now talking of the event 2 on the same latches again. The event has changed, the data has changed to 1 to 2, but we are still talking about the same latches and same combinational blocks. So I will not call it L3, L4. I'm just going to unroll that and call it L1, L2 again. Yeah, that makes sense. Okay. So in order for event 2 not to disturb event 1, what should happen? You remember that in order to sample event 1, data should not change in this window, right? Which means that this change of TCCQ1 plus TCD1 should happen outside the hold window. Correct? So what is the constraint that I can write for that? So by the way, this delay is what? T non-overlap. Okay. So what is the constraint for D2's hold violation not to happen? Okay, think what happens if this T non-overlap is 0. This clock edge has gone all the way till there. Then very clearly this hold window will now move all the way here. Correct? It could move, right? Depending on the delays. So what is the constraint for the hold delay not to occur here? Hold violation not to occur. Change, yeah? Okay, so we have one thing. So let's write it. So going from this clock edge all the way to this delay, I have a delay of what? T non-overlap plus T CCQ1 plus T CD1, right? And on the other hand, I have what? T hold. What is the constraint now? Yeah? T hold should be less than this, right? The change should happen outside that hold window. Okay. So very quickly, tell me what happens now if there is skew. These edges can start moving, right? These edges can start moving. So first come to the max delay constraint. What happens if this edge moves a little bit? Is there a problem? Yeah, if you don't want to borrow time, there's no issue. I mean, there is, yeah. It's basically insensitive to clock skew. Given that skew itself is a very small number. If the deviation from the actual edge is very small, then it is true that max delay is not affected by skew. So therefore, this is what we call skew tolerant. Max delays is skew tolerant. So I'll answer that in the next class. We are out of time. I'll answer that in the next class. But in general, it is skew tolerant. What happens to the min delay? Will it be affected by skew or not? So what is that? What is it that I have to look at? I have to now look at this edge, right? Right? Does it affect it or not? Yeah, it does. Just exactly like how it would affect my earlier thing. I would simply add skew here. Correct? Because now my hold window has moved to the right. If it's skew, this hold window would have moved here. So the point is, non-overlapping clocks is actually giving you a lot of window. That's how you are able to get over this. So if your non-overlap period is large enough, you will not have hold violations at all, as very evident from this waveform. It's only when this non-overlap becomes 0 and phi 2's falling edge almost coincides with phi 1's rising edge, then you will see this violation happening. Using clock and clock bar, yes. Or if your overlap period is very small. Non-overlap period is very small, I'm sorry. Okay. Now remember that for max delay, I have only one constraint. For min delay, this constraint has to hold at every latch. I could do the same analysis sorry, with D2 changing and then analyzing what happens at D1 again. So this condition min delay has to hold for every latch. So how many constraints do we have in a latch based system? One max delay and two min delay constraints, one for each latch. In a flop based system, how many constraints did we have? One max delay, one min delay. I'll leave you with a question. Come back on Monday thinking about it. Flop is made up of two latches, back to back latches. If I split the latches, I'm getting three constraints. If I combine the latches and make it back to back, I'm getting only two constraints. Where did that third constraint go? Okay, think about it and come back.